Hello.
Hi,
Hi.
let's carry on. I intentionally break it down so that it's easier for you if you want to listen to the video.
Again, just sorry.
Intentionally break it down. Break it into two halves so that it's easy when you want to review.
Yeah, so that I won't get scared of the video. I have to go through 1 hour.
Rather than
right?
you have to go through 1 hour, it's better that you can choose the first part is sinusoidal, and the next part is simple harmonic motion.
Yeah, part 1, part 2.
Easier to use. It's on YouTube. So you don't want to download it in your device, you go to YouTube there. It's all in YouTube.
No, usually I'll download easy so that I don't have to buffer.
You too much thing in your computer, it will slow down your computer.
No, Lacha, I'll transfer it to the pen drive.
Okay, let's carry on. You won't bother about all this thing.
Yep.
These days the internet is very slow, don't know why. Okay, we are going to start defining simple harmonic motion properly. Right? Basically, the motion is going to and fro. Right? There's a fixed position where it's at rest. So it's going to and fro. You can call it oscillation or you can call it vibration. It can go up and down. Doesn't matter as long as it's at rest. Go up and down is a spring. It's a mass on the spring. Okay, so anything that repeats itself, we call it periodic. Anything that we can represent with a sine graph or cosine graph, we call it harmonic. That's why we are going to use a lot of sine and cosine graph. That's why I review with you. So simple harmonic motion is just a perfect motion. Right? We don't see it in real life. But usually in physics, we look at something perfect first, and then after that, we modify it. That means it is a motion that goes to and fro forever, which we don't see forever. Right? We do see that when you push your sister on a swing in the playground, after a while it will stop. That is the oscillation. Right? But that's not perfect. That's why I call damp oscillation, which we'll study later on. We'll study oscillation will go to and fro forever. Right? So these are some examples. If you're gone, right? Simple pendulum oscillating less than 10 degrees, that means small angle lah. Mass vibrating up and down, or a trolley between two springs vibrating left and right. Okay, so these are some other examples which you don't need to bother about that, just for your knowledge. And then motion or simple harmonic motion. Right? Example, simple pendulum, a heavy mass, a string. This one we clamp it, swing to and fro in vacuum. We call this free oscillation. That means no loss or gain of energy. Thus, the oscillation is constant amplitude. That means there's no gain energy, there's no loss energy. The amplitude of oscillation is constant. No resistive force, that means no air resistance or no external force applied to the oscillating body. The body is oscillating in vacuum. Right? Vacuum. And in this case, it's just kinetic energy transformed to potential energy and potential to kinetic. The total energy of the system is constant. Right? When we use total energy, we usually think of it as mechanical energy, not the total energy that include work done against friction. No, we are not including that. We are only saying total energy of the system. So the system is the oscillating pendulum, changing from kinetic potential. Stop me if I'm going too fast. Okay, so that's your simple.
Just go back and give me a picture. I'm trying to understand it.
Free
Yeah,
oscillation.
vacuum means free oscillation, what, no resistance, what, right?
Free oscillation means in vacuum, no air resistance.
Yeah. So no loss again of energy. Okay. So yeah lah, kinetic energy equals to potential energy lah. Total energy is constant. So every energy is constant lah, no external forces. Yeah, I understand. Okay.
It's just kinetic change the potential, that's all.
What?
Kinetic
Sorry,
energy changes the potential, that's all.
How? Oh yeah, by moving and then yeah, I don't understand that. Sorry.
You just listen. Right? At the end of the course, you don't understand, then you ask. Basically, you have forgotten all your SPM. Yep. When the simple pendulum is oscillating, it goes up and down. So it goes from kinetic energy at the bottom maximum and goes to potential energy. So we are going to review that.
Okay.
Okay, so that's your simple pendulum. You move from 1 to 2 to 3. Right? Oscillating simple pendulum in vacuum. In free oscillation, the bob displays. Right? Displays means this is the rest position. You shift to the left or to the right. The bob swings between two limits. There's a limit A and C, or 1 and 3. Right? Maximum or minimum displacement. And that center there, B, is called the rest position. Right? Where the bob is at rest. Where the bob is not moving, that's called the rest position. Right? So that's called the rest position. Okay, so rest position or equilibrium position is where the bob is at rest, not moving. Right? So this is a support. You see, you use a clamp to clamp the string. So that's the string. There's a bob, or it can be a heavy mass. Right? Usually we think it as a point. Okay, so if it starts from 2, right, we can show the oscillator, the oscillating object. Right? And then remember the angle is small. Why small? When it's small, then the motion is like a straight line. Right? If the angle is small, it's like a straight line, to and fro, that's all.
Less than 10.
Less than 10 degrees. Right? You can use what you have learned in SPM to help you. Right? When it's at B, right? B is the center there. Where, right? Think of it as the bottom is the ground. Bottom here is the ground. It's nearly near the ground there. So at this part there, the potential energy is 0. Right? You can go to time. So from B to C, and then from C to B, from B to A to B, each of them is a quarter. So from B to C is a quarter. From C back to B is another quarter, so it's half period. And from B to A is a quarter period, so it's 3/4. And from A to B, another quarter, so it's period. So in terms of displacement, if it's at B, it is 0. If at C, it's x0. Right? If it's returned to B again, it is 0 again. Right? If we return to A, it's minus x0. Right? We take to the right as positive, so to the left as negative. Then return to B is 0 again. Right? So at B, right, basically this is potential energy largest. The height is higher, potential energy is largest. Then potential change to kinetic. No potential here if this is your ground level. This maximum kinetic energy. So you should be able to get this table, fill out this table. Right? If it's maximum kinetic energy, maximum velocity, then it's maximum kinetic energy. Then this part will be maximum kinetic energy here. Right? When you move to this part, 0 kinetic energy. Right? When it comes down again, maximum kinetic energy. It go to the left, 0 again. Then it come down again, it's maximum kinetic energy. So if kinetic energy is maximum, velocity is maximum. So velocity in this part, same. But if you look at potential energy, where the kinetic energy is maximum at this part there, no potential energy. If this is at the ground level. And then where the kinetic energy is 0, the potential energy is maximum. This part maximum. This part comes back to 0 again. Right? It goes to that part there. Maximum potential energy. Okay, so sorry, something has gone wrong. Okay, on the wrong thing, that's the problem. Okay, so that is your maximum potential energy where it goes to that part there. And after that, it goes to 0 again. So all these table you should be able to fill up yourself. Right? So if this is maximum kinetic energy, maximum velocity, right? Because kinetic energy is half mv squared. Then 0 kinetic, 0 velocity. Right? And this part, right? It goes maximum velocity goes to 0 velocity, come down, it's going to the left. That's why I put a negative sign there. Maximum again. Maximum kinetic energy, maximum velocity to the left. And after that, it goes to 0 again. Then after that, it goes to maximum again. And come down back again here. Right? The arrow shows the direction. To the right is positive, to the left is negative. Okay, so if the acceleration must be 0, if it's going to be maximum velocity, then to go to 0, the acceleration must be maximum. So that it will become 0. Right? It cannot accelerate anymore. Velocity is 0 here. So acceleration must be maximum here. Right? We will go into the maths involved to show you if you still cannot accept that. Then this part is 0 again, where it's coming here. If maximum velocity moving to the left, acceleration must be 0. If not, it cannot be maximum. It cannot be maximum velocity. And velocity, it decelerate again to 0 velocity. So that's why the acceleration is not to the right. A naught and then 0. Okay, any comment, any question to ask? This is your SPM work.
Yes, I have a question.
Yep.
Okay,
What's your
kinetic
question?
energy and potential energy, right?
Mm.
Technically, is conservation of energy. That means it's total kinetic energy plus total potential energy is the total energy we have. Correct, right?
That's right.
So let's say the B at the beginning, the number 2 technically is B, right?
Number 2 is just total energy equals to kinetic energy. That's all. Right?
Yeah, okay. No. Which is the B position? Number 2, right? Correct, right?
Now, you cannot say peak position. It's the
B,
ground level,
B.
number 2. Number 3 is
B.
maximum potential energy.
Yeah, okay.
Number 2 is
So
maximum kinetic energy.
No, then the 1, 2, 3 is to compare from the BCBAB or
It's
the
just
up
moving
one.
to and fro. Different time, the pendulum will at different position. That's all.
So what I'm trying to say is because total energy means is equals to kinetic energy plus potential energy. Correct, right?
Yes. Every time there. We
So
are looking
if
at two
kinetic
extremes.
energy is max, confirm potential is 0 lah, because already max what kinetic potential no need what, right?
If the kinetic energy is maximum, there's no more potential. If the potential energy is maximum, there's no more kinetic.
Vice
That's all.
versa. Yeah.
We are looking at the two extremes.
Okay. The accelerate okay, kinetic potential is just the opposite each other lah. Which one highest and then which one is 0. That's it. Right. Correct.
Yeah, it just changed to kinetic to potential. We are not looking at the center there. Right? We are looking at the two extremes. Center there will be kinetic and potential. In between will be kinetic and potential together.
So okay. So no. So I want to ask. So at number 2, right, teacher?
Yeah.
Number 2, kinetic is maximum or zero?
Kinetic energy is maximum. Is at the ground there. Is at the highest height. Right? 2 is ground. Highest height. Potential energy is largest. You swing to
Oh
2.
yeah, because it's stopping, then
Lowest
it goes
lower
back.
ground. At the ground there. No height. So potential energy is
Because
0.
number 3 is slowly stopping, that's why it's potential energy at highest lah, right?
Yeah, no, kinetic energy at number 3 and number 1.
Kinetic energy increases when the thing speeds, right? Correct.
When your kinetic
Okay.
energy is maximum, potential energy is 0.
Okay. The middle B, right, teacher?
B is where the kinetic energy is maximum.
Yeah,
It's
no,
ground level.
okay.
Just imagine it's
No,
on the
you
ground.
said the first B starts from B naught. Okay, that means at positive lah because it goes to the right. So
Yeah.
0. Okay. Okay, and then you go back B. Yeah lah, obviously lah because left means negative lah. That's why negative lah. And then
As
you
you
go
move,
to A is 0. Correct. And then you come back is positive lah. So positive, negative, positive back. Correct.
yeah. You just look at the table, understand the table.
Okay. Displacement, in terms of displacement, the B is, why displacement 0? So that's why I don't get it.
0 is called
Why,
0. B is called 0, where we start. That's rest position.
Okay. Yes.
And then this is the largest one. We call it amplitude.
Oh,
X
okay.
naught.
Okay. All right. Yeah. Oh, okay. So that means the moment you start the start place, that's why the displacement is 0 lah. Right. Always. Hello.
Yeah. Just understand the table.
No, the place you start, technically you start from B. That's why all the places at B
It's
is
written
0 lah.
there. It's shown there 0. So you have to accept it's 0. That's the starting
Only
point.
time will change.
It's normal linear motion where it go one direction. This is going to and fro. So there's a 0. And then you move to the positive side. After that, go to
X
0. After that, go to the negative side.
Okay. Got it.
Then it
All
comes
right.
back to 0.
One
So you
more
need
thing,
to know how.
okay.
Yeah.
Yeah. Okay, time is 0, understood. And then C, you can make it 1T also, right? So 1T, 2T, 3T, 4T also, right? Technically.
You just call it a point, that's all. That's why we call it ABC. Just a different point, that's all.
No, the
It's
time can be any
vibrating to and
factor.
fro. You go from B to C, C to B, B to A to B. That's all.
Yeah, okay. But it can be technically also 1T, and then the B can be 2T, and then 3T, 4T also can, right?
Don't bring in to confuse yourself. Just follow what I have written down there. Don't 2C, 1C, 3C. No, don't confuse yourself. I just call it a point. I give you a number. I call it a thing that you can, so that you can see where is the B, where's the C, where's the A.
A point. Okay.
It's just a point.
Okay. The acceleration part is the one I don't understand.
Don't worry about acceleration part. It has to be 0 here.
Of course.
And then since it's 0, it must be the largest here.
Why negative, not positive, man? Because
Negative,
you're going to the
because
right.
it is going to be positive. It's going to accelerate it. So it will stop it with maximum acceleration here.
What?
If it's positive, it will still accelerate. That's why it must opposite to decelerate it. So from here to here, the velocity is decreasing. So it means that the acceleration must be increasing here to stop it. Acceleration is normal constant. It's increasing. From B to C is increasing.
Yes.
Opposite to the velocity. That's why it's deceleration here. From B to C is deceleration.
Oh.
Cannot understand, don't worry.
Just,
If you go to the maths involved, then you will probably see the thing more clearly.
No. So just remember like this, B to C, if the velocity increasing means then the acceleration decreases lah, decelerating, that's it.
Yeah,
right?
acceleration must oppose the velocity so that the velocity is decreasing. If it's in the same direction,
because it's slowing down.
If the two arrows are in the same direction, that means it's acceleration.
Okay.
If the two are in different direction, it means deceleration.
All right. Okay, can go next one. Can.
Right? So the body oscillating, we call it oscillator or oscillating particle. Right? We think of the bulk as a point mass or particle, and the string of negligible mass. Okay? We won't bother about the string. And then some symbol we use, x is displacement. That means distance move from a fixed point. Right? V naught, the naught there show maximum velocity. A naught show maximum acceleration. EK naught means maximum kinetic energy. EP naught maximum potential energy. T is the period. Right? That's where I just told you just now the time. Right? If the time, the period is from B to C to B to A and back to B, that's called the period, the time, T. Time to move from A to B, right? A to B, and then from equals to from B to C, and then from C to B, and back to B, and also from B to A. All these, each of them is a quarter of the period. It's the same. Right? These are memory work. What is an oscillation? It's to and fro motion between two limits. That's your limit. A and C is your limit. B is the rest position. So one oscillation or one cycle is one complete to and fro motion about the center point. Center point is the rest position here, or between two limits. The limits are your A and C. Right? So oscillation will be from A to B to C to B to A. That's one oscillation. Or you start with B, it goes to C, it comes back to B, it goes back to A, it comes back to B. Okay, that's one oscillation. Right, so the time to go from B to C, back to B, and B to A, and back to B is called the period. And that is the time for period, is the time for one complete oscillation. Okay, nothing much.
Wait, so
understand it and memorize it.
Okay, so period means is from A to B to C and then back to A. That's basically period, right?
You always must start from the same point. And then the time to start from the same point and go back to the same point is called a period.
So one oscillation is similar to period lah, technically, right?
I don't know why you have so much problem. We have defined that so many times already.
No. I just want to clarify. So sorry if I'm asking.
And you study in your SPM. I don't think why you should have all these problems.
Yeah, I didn't focus properly in SPM.
It's so clear here. Where is your oscillation? Or this one? And that is called your period. It's a memory work.
It's the same thing lah.
Nothing that's the basic formula, basic thing that you must remember. Just like English, you have to know vocabulary. So these are the definition you need to know. Period is not from B to C. That's all. It's not the time from B to C. It's B. If you start from B, it goes to C, goes back to B, goes back to A, and goes back to B. That's called the period. It's the time. Right? Frequency of the oscillation is the number of complete oscillation per unit time. I mean the number of oscillation in 1 second. Right? Count 1 second to be oscillation. And that's usually hertz or cycle per second, or it's just per second.
Yep.
That's a unit. How it's related to T is 1 over T. F is equal to 1 over T. Amplitude, right? You can use X naught, you can use A, or some book will use R, is the maximum displacement of the oscillator from the rest position. So in this case, it's from B to C is the amplitude, or B to A is amplitude. Okay, nothing much, just memorize only and know how to identify what's the amplitude, what's the frequency. Okay, so that's the amplitude. Rest position, right? Or some book will call it equilibrium position, where there's no forces acting when it's at rest. That's called the equilibrium position. Position where the object, when it's not oscillating, when it's at rest, when it's not displaced. So that's the rest position, B. Then angular frequency, right? We study circular motion, we call it angular velocity. But here we cannot call it angular velocity because it's not turning any angle. So we call it angular frequency. Same, omega. Right? It's just a frequency expressed in radian per second. Right? Omega is 2 pi f, same as your alternating current. F is the frequency of oscillation. Right? This is one oscillation. So one oscillation is 2 pi, that's why it becomes 2 pi. Because we want omega as radian per second. Okay, let's start with kinematics of simple harmonic motion. Definition. Right? Your book slightly wrong. Right? But you must follow this one. The book gives two different definitions. Is in the syllabus, you have to accept this definition. Simple harmonic motion is defined as the motion in which the acceleration is proportional to its displacement from the fixed point. It's always directed towards the point. Memorize this. Right? In terms of formula, right? A is vector acceleration, X is the displacement, and because of they are opposite to each other, always opposite to each other, we put a negative sign there. And then this is a constant. We call it omega because it's related to angular frequency. That's why we call it, instead of calling it K or C, we call it omega squared. Right? So we can either say always directed towards the point, or we can say acceleration and displacement are always in opposite direction. That means they are always opposing each other. Okay? Anything that you want to ask?
Okay, just now the super harmonic motion
It's
was
just
a
a lot
different
of terms,
definition.
a lot of
Another
formula you
one.
have to learn to accept and learn how to use it. Right? That's why.
So this is another simple harmonic motion definition and formula.
So
right?
as long as it obeys this equation, then it's called simple harmonic motion.
I mean, this is a different definition, correct? Right.
This is just to define you properly what we call simple harmonic motion. As long as the acceleration is proportional to displacement, and the acceleration,
the keyword acceleration is there.
Right? Acceleration and displacement are always opposing to each other, then that is simple harmonic motion.
Okay.
Okay? Just memorize it.
Oh, according to the formula lah.
And then memorize the formula and know how to use it.
No, the W square X is the displacement, W square is the acceleration, right?
A is acceleration.
Yes.
Right? We call that omega.
X is the
it's not W, it's omega. Yep. It's a Greek alphabet. It's a constant, this one, that's all. Think of it as a constant. Instead of 9, I call it 3 square. It's all right. And this is your displacement. X is a vector. Okay? Right? And this is a differential equation. And these are the solution. Right? This acceleration, you can rewrite as dv dt and d2x dt squared. Right? That's why we call it differential equation. So these are the solution. It can be this solution or it can be a cost solution. Okay, let's derive it. Let's show that your x equals to x naught sine omega t is a solution to this differential equation. Right? We differentiate this equation. Right? We treat this as a solution. Right? We start with suppose that is the solution. Then we differentiate it with respect to time to get your velocity dx dt. Right? So that's your x naught. Differentiate omega t becomes omega. Differentiate your sine omega t becomes cos omega t. Then x naught omega, we call it your V naught. Right? This is a maximum value like your circular motion. Circular motion, we use radius. So this is amplitude, that's all. Then you want acceleration. How the acceleration changes with time? We differentiate the acceleration. Right? Sorry, differentiate the velocity. So this is the velocity. Differentiate it again. Right? X naught omega. Differentiate your omega. Right? It's a cos. So cos omega t becomes sine omega t minus sine omega t. And differentiate your, okay, you have to start in 10 minutes time. Differentiate your omega t, we get omega. So that is omega naught omega. So there's another omega. That's why omega squared. So that is your acceleration A naught. Or right, we can see that your x equals to x naught sine omega t. Right? Take your x1, x naught out. Sine omega t, we can rewrite that. Becomes minus omega square x. That's how we show the solution. Substitute into the equation. If it comes out as a solution, then we have shown it. Okay? Nothing much. As long as you understand it, know how to derive it, that's all. Anything don't understand?
Yeah. They said show that x equals to x naught sine omega t is a solution to the. So that means they want from that to the acceleration. They want to change it.
They want the solution to this differential equation. So yes, there are many ways to show it. You can differentiate this one to get back this equation. Then we have shown it. That's what we are doing.
So okay, no. So first you use v equals to dx over dt, right?
We just find acceleration, differentiate 2 times. First to get velocity, then to get the acceleration. Okay. You don't have much time already anyway. You have to digest it yourself.
No, I don't understand the derivation.
You go back and think about it. It's very straightforward. We just derive this equation. If you understand, it should be no problem. Differentiate that dx dt, that's all. We get that one. Then after that, we differentiate dv dt. That's your v. That's why we get this equation. Then we replace your x naught sine omega t as your x inside here. We still got omega squared, that's all. So we have got the original equation back, this one. So we have shown it, that's all. As long as you can understand the maths, now go back and study yourself. We don't have time to wait for you. Okay? Anything you don't understand, you ask. All these are your maths as well.
Okay, teacher, send me the slides.
Of course, I've been sending you all the slides. You don't need to tell me. Just understand it. Right? X naught is the amplitude of maximum displacement. Omega is angular frequency in radian per second. And that is the equation that we are looking at. X naught sine omega t. So if you draw the graph, amplitude is x naught minus x naught. Right? That's your period t. That's your half t here. Right? You should be able to draw the graph for this one. And that is where it starts oscillating, maximum velocity there. Okay. Okay, I think we have to carry on already. We are behind time already. So you must be able to recognize. I start with B. That's the point B. Then where is C? C is here. You can identify here, or you can identify here in terms of time. Then where's your B? There's your B. That's where your B is. Then where you go to A, where's your A in the graph there? There's your A. That part there, the center there. Where you got your minimum point. Then where you come to B, it goes back to one period. That's all. Right? There's your B here. And then you just need to know your basic maths formula. Instead of T, we use omega theta as omega T. Then omega is 2 pi over T. Same as your AC, that's all. Okay.
Okay. Yep. All right. Anything means I'll ask you.
You go back and review. So if you
Yep.
start from C, right, where you start from maximum always is a cos graph. X naught cos omega T. If you start from C, then your graph is there. Right? So the equation, if you start from rest position, is X naught sine omega T. These are the maths that you need to know. Right? Cos 0 is 1. Cos 180 is -1. Then your sine, right? The trigonometry formula. So all these you can review yourself. So you start from maximum amplitude. Then it's a cos graph. Okay. Then you can rewrite that. You like it's still a sine graph, except that you have a phase there. If you call that 0, then this is pi radian, pi over 2, half pi radian here. Okay, sorry, you have to go a bit faster. You just review it yourself. Don't know, you can ask the next period. When is your next period that you want?
I'll inform you, Jah.
Okay. So where you can imagine where you start from 0 moving to the right, you can imagine that that is your pointer, 0 degree. So you move to C, that's 90 degrees. You move to that part there, back to B means minus is 180 degrees. Move to A is 270 degrees. If you move back to B again, then it's 360 degrees. Right? Or remember this 0, half pi, pi, then minus 3 pi over 2, then come back is 2 pi. So we can write the general equation. Right? Put a phi there. Right? So basically, we call phi as phase. Right? Locate where it starts. If we use sine. Right? If it's 0, it start from here. If it's half pi, start from here. Right? What happens if what is the equation if we move from B, if we start from B and then move towards A, what's the equation?
What's the one, Jah?
What's the equation if the object start from B and move to the left?
Oh, negative x naught
What's the equation?
sine. Negative
correct.
x naught sine.
Right? Negative x naught sine omega T.
Because moving to the left, negative.
Right? So the phase describe the point that an oscillating mass has reached within a complete cycle of the oscillation. So you just memorize it. I just explained to you just now the phase, where it starts. Right? Phase difference between two. Right? What's the phase difference? Phase difference between two oscillations show how in terms of radian they are out of step. One step behind the other.
What do you mean out of step?
AC. Okay. Anyway, we will explain to you. If you don't understand, I have to stop in a while. The time is almost up already. I think I will stop here. Anything you try your question. Sorry, we don't have time to try out some question with you. Can try the checkpoint, can try the worksheet that I've given you. I think the next period I will try with you. You just tell me when you want the
It's
period.
okay. Yeah, okay, can.
I was hoping to finish it today, but you cannot. Doesn't matter.
It's
So we
okay,
stop
okay,
here. You stop here. Have a good day. Remember to review it.
Yes, you too.
Okay,
Thank you.
bye-bye.
Bye-bye. Bye.